So we're just going to move the sorting notes up near the top of near the rest of the notes on the page. Okay, right. From there. Okay, so tonight we're starting our last topic. The topic is sorting algorithms. We look at sorting algorithms in first year as our final topic for two reasons. One, it is in the same way that we look at the idea of objects and classes. And I said, look, we're going to do a little bit now, and then we're going to come back to it when we get to second year. Same idea with sorting algorithms. Sorting algorithms are considered to be classic algorithms. No matter what programming language you're in, there are implementations of sorting algorithms, because sorting is a really useful task we can get our computer to do. If you think about what computers deal with, they deal with huge amounts of data, they deal with huge amounts of information at any one time. And for us to make use of it, it's very sensible to have it in a particular order. Now, we've all been to Amazon or to eBay or to any online shop, and we see that we can sort that information by price, low to high, high to low. We can sort it by name, A to Z, Z to A. We can sort it by best match. And if we get best match, or we get best popularity or recommended, there's extra algorithms built in there. But essentially what we're looking at there is taking a bunch of data and shuffling it around so it matches a particular order that we want to maintain. So it's really useful for us to be able to do that with our information. As we move from first year to second year, you will start to see how much more information we end up dealing with. So in first year, we dealt with reasonably small amounts of information. We didn't really have any huge files to deal with. As you go into second year, you'll deal with slightly larger amounts of information. As you go into third year, even larger again. We get to fourth year, especially if you're looking at something like the data analytics and visualization, you're dealing with very large data sets. And so our understanding of how the data is shaped is quite important. So that's why we're looking at that. There are loads of sorting algorithms. Sorting algorithms start off really, really basic, and for this year we're looking at 3 really basic algorithms, and they get more complex as we move through the degree, as we get more comfortable with programming. But all of them essentially, and you'll see when you see the source code in this, they all utilize really basic elements of programming. They utilize loops, swapping numbers around, and if statements. So that's kind of all they utilize. So here's a quick summary of what sorting is, unless in case anybody didn't really know. If we had an array of values going from A0 to AN-1, we would want to reorder the information so that A0 is less than A1, A1 is less than A2, A2 is less than A3, and so on. In other words, the smallest value will be at the very beginning, and the largest value will be at the very end. For example, something like this. That is a sorted list. We go from unsorted, where some elements are in the right position, so 4 should become before 5. However, some are not, so 5 should not be before 2. And we shuffle them so that we have a complete sorted list. Every number is smaller than any number on its right-hand side, and every number is larger than any number on its left-hand side. And that's how our definition of what sorting is. So that's basically to say it's very important that we can sort information, because when we sort information, we can utilize it, we can access that information, we can deal with it quite simply, we can do it much more efficiently. We're going to look at 3 sorting algorithms this year. We're going to look at 1 this week, and it's probably the week that takes the longest, which will be selection sort. And it's going to take the longest not because it's the most complicated, it's actually easiest of all of them, but once you see how selection sort is done, doing bubble sort, which is the middle one we look at, or insertion sort, the last one we look at, they all become slightly easier, because you understand what we've done previously, and this is a small amendment to the next sorting algorithm. We're going to talk a little bit about the complexity of them, just so that you understand as we go into second year what that means and how we can improve that complexity. We can make them less costly for our computer. They run in a smaller space, they run in a smaller time, they take up less resources on the machine. And that is a huge problem or a huge challenge for a programmer. When you're writing a program, does it do what the customer's asked it to do is kind of your minimum requirement. So you all are working on an assignment for me at the moment. In the reality of working as a programmer in your career, the spec that I've given you, all of the features I want implemented, that's kind of a minimal viable product. That's the minimum I expect. And where you as the programmer are going to go above and beyond, or would go above and beyond, is where you can get the same program to run X% faster, or in a smaller space, or it takes less processing power, so it runs more efficiently. And that's where you can separate yourself as a good programmer, as an advanced programmer, when you're able to look at a piece of code and go, yep, it does everything it's meant to do, and I've taken this section here and I've optimized that section, I've optimized this section here, and I've optimized this section here. And it's never going to be one change. It's never going to be one algorithm I'm going to change, and all of a sudden, 1,000 times faster running. It'll be a little segment over here, a little segment over here, a little segment over here. The larger the system, the more of those little segments you'll have, but they all kind of accrue in time. And what we want to do is not just solve the problem, but solve the problem at scale. Okay. In computer hardware or in foundations of computing, have you talked about NP complete problems? No. Okay. So the biggest challenge that we have at the moment in computing is something called an NP complete problem. And essentially, what that comes down to is there are a category of problems which us as humans can solve them faster than, so we can solve them and verify the solution faster than the computer can, just the way the information is stored. And one of the current research areas in computing and computer science as a field is optimizing those problems, optimizing it in a way that, okay, I can not only solve the problem, but I can verify it. And I can do that in a faster time. And if I go from, let's say I've got 100 elements and it takes me 100 time units to do that, well, then that means if I've got 1,000,000 elements, it takes me 1,000,000 time units. And if I've got 10 million elements, 10 million time units. And those time units might be milliseconds. They might be nanoseconds, but that all adds up. Okay, so that's kind of what we're looking at here. So the reason why we want to sort information, the reason why we want to look at these algorithms is to introduce you to the idea of sorting. That's really useful as a programmer, but also to introduce you to the idea of, hang on, I can see that that's going to be costly. That's going to be expensive to run on the machine. And as you get more competent, as you cover more content in programming, you'll be able to go, do you know what? We don't have to use selection sort. We can use merge sort or quick sort or heap sort. And they're different, more advanced, more complicated ways of sorting. But as with nearly everything in programming, if you want to make something faster, it usually means that you, the programmer, has a bigger challenge in understanding what's happening because it becomes a more complex solution. The computer is able to run it much quicker because you spent the time thinking through it and very often looking at the mathematics. Okay. So selection sort is the first sorting algorithm that we're going to look at. It's very, very simple algorithm. It's also called sometimes a common sense sort. And what you're going to do is you're going to take an array. In this array, you do not know the state of the information. You are not given any other information apart from, here is an array of integers. Everything we're going to deal with here is going to be integers. And so what you do is you say, all right, let's figure out what I have to do. And you're given a little bit of description. You said, well, I want it to be ascending sorting, which means that every element is going to be smaller than the element on the right-hand side. It's going to be growing in numbers, 1, 2, 3, 4, 5, 6, 7. That's ascending order. We have a different type of sorting algorithm or different type of sorting order called descending, which is the opposite. 7, 6, 5, 4, 3, 2, 1. It's going down, it's getting smaller. But we're going to go with an ascending. So what you're going to do, what your algorithm is going to do is say, take the current position I'm in now, so index 0 to begin with, check every element to the right-hand side of that position, and see if there's any value that's smaller than where I am now. Tell me the location of the smallest value inside the unsorted section of the array. So we start at index 0. I'm going to check from index 0 plus 1, so from index 1 all the way to the end of the array and find the smallest number. If you think about all of those questions we did when we were looking at arrays, get you to find the smallest number, get you to find the maximum number, get you to find the location of the smallest number. I was getting you to do those because I knew this was coming down the line. Once we get to the end of the array, we go, all right, I've checked every remaining element in that array. I know where the smallest number is. And I take my current position and the location of the smallest value, and I swap them. So I move the smaller number near the beginning of the array. And then I move on to the next index. So index 0, guaranteed that's the smallest number there. Let's move on to index 1. Let's find the second smallest number. And the algorithm repeats. I'm at index 1. I'm going to search from index 1 plus 1, so from index 2 to the end of the array to find the next smallest number. Search all the way to the end, find the smallest number, swap those values. And then we move forward again, and move forward again, and move forward again. Notice? So in that array, in that algorithm, if I was to pause it at any time, and I'll run this through Jelly so you'll be able to see it working. But if I were to pause that algorithm at any time, no matter how big the array is, no matter what order the values are, and remember we have the advantage, especially if I put it in something like Jelly, you can see the numbers. So you can see where I am, what's on the left-hand side and what's on the right-hand side. But what I can say is at any point, every number on the left-hand side of where I'm searching is guaranteed to be in the right order, it's guaranteed to be sorted. And every number on the right-hand side, the only thing I can say for certain is I haven't checked it yet. So we consider that unsorted. Now it's possible, and you'll see in one of the examples I'll do, it is possible to have all of the numbers already in the right order. And so your algorithm does the same check over and over and over again for nothing, essentially. And that's one of the big disadvantages of the algorithms we're going to look at this year, is they're not aware of the information, they're not aware of the data we're dealing with. So we can't say anything about it apart from, here's the array, check if it's sorted. And the only way I can check is by going through every element and performing this algorithm over and over again until I reach the end of the algorithm and go, yes, now I can guarantee it's sorted. If I accidentally run the algorithm again, it doesn't have any prior memory of that. It goes, all right, and it goes off and checks every element to make sure it's sorted again. So there are definitely disadvantages to the algorithms we're looking at, but we start off with simple ones, the ones that are easy to get your head around, and we get progressively more complex as we work our way through. Okay, so the algorithm is this. Find the smallest element of A, swap it with the element in the first position of A, find the next smallest element of A, swap it with the second position of A, and continue on until you get to the end of that array. That's a really simplified version of the algorithm. What that looks like in code is this. We are going to have a loop that's going to go from 0 to the length of the array minus 1. Now that minus 1 is important. If you don't include that minus 1, you're going to have crashes. And we'll go through the reasons why the crashes are in a moment. You're going to have a variable here, in this example here, it's called smallest block or smallest location. And we're going to set that to whatever the value of x is. So we start off at 0. So that's, I've only looked at one number. This has to be the smallest number because I haven't checked anything on the right-hand side. And what I need to do then is to go and check and verify, is this actually the smallest number? So to do that, I have the inner loop. And the inner loop is going to start from wherever I am, plus 1. There's no point in checking the same position. There's no point in checking x because I already have that value. So I'm going to check x plus 1 and work my way to the end. And this loop here goes all the way to the end. The reason why we've got minus 1 here is because y is set to be x plus 1. We went all the way up to a dot length. The plus 1 would crash our program because you get an array index out of bounds. You have 5 elements in the array. You end up trying to access the 6th. For every position I look at in the inside loop, I'm going to say, is the value in element y smaller than the value in element smallest location? Have I found a new smaller number? If I have, brilliant. Y is now set as the location of the smallest number. And I keep checking. So as we were to go through this loop, we may change the value of smallest location several times as we work our way through. Because we might find another smaller number, and then another smaller number, and then another smaller number. When the inner loop finishes, we have checked every value from where I started, x plus 1, all the way to the end of the loop. So I know exactly where that smallest value is, and then the last thing I do is I swap the value in AX with the value in the smallest location. So I move the smaller number to the beginning of the array. And then I move on to x goes plus plus, so I move on to position 1, I do the exact same thing again. That is selection sort. Does anyone, based on the code we have on the board there, does anyone have any questions? Does that make sense? Yeah? Or at least no one's screaming no, so that's a good start. Okay, so we are about halfway or half an hour into the class now. The remainder of the class is us testing. Do we actually understand that? If it ends up that everybody's 100% on this, we will start onto the next algorithm. But the way usually I'll do this is I do one algorithm per week. So one algorithm this week, next week, and the week after. And then we'll be back the week after term finishes. So on Tuesday the 6th of May for a revision class before the examination. But if everyone is flying with this content, we finish it a bit earlier, well, then we'll have 2 revision classes. Okay, let's look at an example. Let's look at a couple examples. So we're going to start off with this example here, and we can see that these values are not in ascending order. Okay, they're actually in reverse. They're in descending order. This is the worst possible scenario for our algorithm, because we will be doing that swap calculation over and over and over again. So what's going to happen is we're going to take the value of 9. And we're going to then, so that's the outer loop, because right, that's the smallest location here in position 0. The smallest value is 9. And then our inner loop starts from x plus 1, so position 1 we check. Is 8 smaller than 9? It is. Okay, this is the new smallest value. Is 7 smaller than 8? It is. Okay, this is the new smallest value. Is 6 smaller than 7? It is. 6 is the new smallest value. Is 5 smaller than 6? It is. 5 is the new smallest value. Is 4 smaller than 5? It is. 4 is the new smallest value. Index 5 is the smallest location. We have reached the end of a loop. Okay, so that's one pass through the inner loop. We now know with absolute certainty the location of the smallest number in that entire array. And what we do is we swap this with the value we want to position. So you can see that 4 goes into position 1 and 9 gets put into position 5, or sorry, into position 0, position 5. Okay, and we repeat. 8 is the smallest number. Is 7 smaller than 8? Yes, okay, this is the location of the smallest number. Is 6 smaller than 7? It is. Okay, this is the location of the smallest number. Is 5 smaller than 6? It is. Okay, this is the location of the smallest number. Is 9 smaller than 5? No. We have reached the end of the inner loop. This is the location of my smallest number. I'm going to take this value here and swap it with the value here. So 5 will go to position 1 and 8 goes to position 4. Okay? We move on. Nope. Sorry. We move on. So right, we're now trying to place index 2. 7 is the smallest value in that array. We start searching from 1 plus the location of 7. Is 6 smaller than 7? It is. Okay, 6 is the smallest value. Is 8 smaller than 6? No. Is 9 smaller than 6? No. Okay, I've got to the end of the array. This is the smallest value, so I'm going to swap these two values. And I get this. So if we look at that slide for a minute, you'll notice that the position of the numbers in this bar, this bar, and this bar are all the same. And we've hit upon one of the big problems with these type of sorting algorithms. I have done 3 iterations of my loop, and I'm done. The numbers are now all in order, because I, as a human, have the advantage of being able to look at the numbers and go, oh yeah, that's simple. But the only reason why we're able to do that, why you guys in the class are able to look up and say that, is because we only have 6 numbers. If I had 6 million numbers, it would be much harder for me to glance and go, yeah, they're all in order. So all of these examples seem very, very trivial, because you can glance at it and go, well, I can obviously see they're in order. But we have to think about scale. We have to think about, we're not sorting 10 numbers, we're sorting 10,000, we're sorting 100,000, we're sorting 1 million numbers. It is still absolutely possible that we could have a 10 million element array, and it's only the first 2 numbers that are out of order. And our algorithm will go around and around and around and around and around for all of the remaining values. That's absolutely possible. Unfortunately, there's nothing we can really do about that. So you can see that what happens now for the remaining elements of the array is we're saying, okay, I want to place this as the smallest number. 7 is the smallest number left in the array. Is 8 smaller than 7? No. Is 9 smaller than 7? No. Okay, that stays where it is. 8 is the smallest number in the array. Is 9 smaller than 8? No. That stays where it is. And because of this swapping function that happens, we don't actually need to go all the way up to the last index. Because if you think about the previous example, I have 6 numbers here. When 5 of them are guaranteed to be in the right position, automatically the 6th one has to be in the right position because there's no other place for it to go. Okay, so that's where the -1 comes into it. Because we know that because we're swapping, because we're always checking on the right-hand side, once this value has been put in the right position, there's only a single value left, which means it only has, or sorry, it does not have any option to go anywhere else. It has to be in this position here. Everyone still with me? Yeah? Okay. We'll look at another example here. So we have our 5-element array. Now this is slightly better for us because they're not in reverse order. Reverse order is the absolute worst case, because it means that you are swapping a huge amount of numbers as you go through it. If the numbers are already in order, the inside of the if statement never runs. So it's it does kind of reduce the cost a little bit for us. But if you have a look here, we're trying to place the smallest number. 56 is the smallest value so far, then it becomes 43, it stays as 43, it becomes 12, it stays at 12. So we move 12 to the first position, and we move 56 to position 3. We're trying to place the next value now. So it starts off as 43 is the smallest number, it stays the smallest number, it stays the smallest number. 23 becomes the new smallest number. And so we swap the value inside here, which is index 4, with the value inside here, which is index 1. So we have 23 here and 43 here. Let me see if we get that there. It's actually here. 78 is the smallest number, 56 is smaller, 43 is smaller. So we end up swapping 43 with 78, and we're left with this. And again, at this point, we can see the value is, or the array is in the right order, but we don't have a huge amount of checks left to do. So this is a better scenario because we actually need to sort more numbers for us. Okay, let's hop out and have a look at a little bit of code. So what I'm going to do here is I'm going to create a quick integer array. So int I'm going to put in values in it. Okay, so random values in random order. What I'm going to do is I'm going to create my loop. So I'm going to have 4 int I is equal to 0. I is less than a dot length minus 1. And remember, we're going to minus 1 because my inner loop goes the position of I plus 1. And this would be I plus plus. So I'm going to get this working properly first, and then I'm going to break it by removing the bits that students often forget when we're implementing this. Inside here, I'm going to have a variable called smallest. Let's go SML for smallest, and set that equal to I. The reason why we set it to I is because that's the position we want to place. So if I set it to I to begin with, it means that before we do any searching, my current number is going to be the smallest number. And what my inner loop is going to do is disprove that or verify it, depending on what's the case, but it's going to check to see if there are any smaller numbers in the right-hand side of where I am, the right-hand side of I. So my inner loop here is going to be for int j, which is going to be equal to I plus 1. And j is going to go while it is less than a dot length. And j plus plus. Okay, so this loop here is the outer loop to place values. This is to keep a record of the smallest location. And this here is to check every unsorted value. So when I say unsorted value, I'm talking about anywhere on the right-hand side of position I. Okay, so at the very start of the loop where I is equal to 0, everything on the left-hand side is sorted, in other words, nothing, and everything on the right-hand side is unsorted, in other words, the entire array. When this loop finishes, every value on the left-hand side of I will be sorted, so everything is at the very last value, and everything on the right-hand side will be unsorted. But if we only have one value, it only has one block or one slot to fit into, so we could say that that's also sorted as well. Inside my loop here, I need to check if I have found a smaller number. So I'd say if, a j is less than a small. So if this is true, it means that the value inside position j, whatever value that is, so if we imagine here we start off and we say 2, which happens to be the smallest number there. So no, it'll check and see, is 6 smaller than 2? No. Okay. Is 4 smaller than 2? No. Is 6 smaller than 2? Still no. Is 3, and it'll work its way through that as it's working this way. When we get to the second value, it'll start with 6. And it'll go, is 4 smaller than 6? In that case, this would be true. So what we need to do then is we need to change the location of our smallest. We initially thought it was here in index 1. But we've now found that it's at least at this point in my algorithm, it's here in position 2. And later on, I'll say it's here in position 3. Not 3, 5. So it's, or sorry, yeah. Position 4, sorry, index 4. So we need a way of recording that. So if we have found a smaller value, what we do is we change our location. We don't actually care about the value. We care about the position where that value is. So what we're going to say here is small is equal to position j. Close that up there. And I close off my inner loop. So all my inner loop is doing is saying, hey, are you a smaller value? Are you a smaller value? Are you a smaller value? And if it ever finds a value that is smaller, it keeps a record of that. It goes, oh, this is now the new smallest value. When the inner loop finishes, I know the location of the smallest value in the unsorted section of the array. on the right-hand side of where position I is. And so what I want to do here is I want to swap it. So I'm going to create int t is equal to a I. A I is equal to a smallest, and then a smallest is equal to t. So put the small value in the correct position. Okay, before I run this, let's have a look at that block of code again. Okay, just look at, fine, it's a combination we haven't seen before, but look at what it is. Here's a loop that's going to start at 0 and run to almost the end of the array. Here's a variable, and we're putting the value inside it. Here's a loop that's going to start at almost the beginning of the array and run to the end of the array. Here's an if statement to see if one number is bigger than another. Here's changing the value of a variable, and here is the algorithm for swapping numbers. Probably the second, third question I got you to do when we introduced the idea of variables. So if you think about all of the little questions I've got you to do, whether they be through workbooks or in class assessments or through your assignments, we have done lots of loops that navigate through the array. We've done lots of questions where we need to take a variable and put a value inside it. We've kept track of if one number is bigger than another or smaller number, and we've recorded it that way. And we swapped two numbers. So all of the component parts of this algorithm you have done before now. The only difference between that and now looking at that as here is selection sort as an algorithm is the arrangement that you put them in. And that's going to be the challenge for you when we get to the examination. Identifying or remembering what is bubble sort compared to what is selection sort compared to what is insertion sort. How do I write one instead of the other? The basic understanding of how to sort numbers is simple. If I gave you a list of numbers, say, okay, sort them into ascending order, and you understood what the word ascending is, or you were able to look up what it was, and okay, right, I know how to do that. Every one of us will do that right. But when I ask you to sort it using a specific algorithm, that's what the challenge is, and remembering how it is. But there are tricks to remember that. Okay, let's run this and see what it looks like. Okay, so here we're going to create our array. It's got 10 elements. So the 10 elements go up there. We add them in. And now we're going to go into our loop. Our loop's going to start at 0. It's going to go to the length of the array, which is going to be 10 minus 1, which will be 9. And just to highlight here, step that on next bit. Okay. So we're checking to see if the value, let's slightly out of focus. So we're checking to see if 0, our current position of I, is less than 9. So not equal to 9, because if we had a normal loop that would go all the way up to the end, we go up to the value of 9, because we go up to, let's say, less than the length of the array, so less than 10 if it was index 9. We're going to go to less than the index of 9. So this is the last index for the outer loop we'll run. Okay, because we know that if we do it from here up to the top, this position here is guaranteed to have the right value inside it. So we're in a loop, then it's going to run. It's going to create a new variable for us called SML. It's going to add in the index of I. We're going to create a new variable called J, and that's going to be I plus 1. Let's start out as 1. And that loop's going to run while the value of J is less than the length of the array. And we're going to check, is the value inside AJ, so a 6, smaller than the value inside A small, which is 2? No, it isn't. So we move on. Keep going through. So essentially what's going to happen now, and remember for the first time around, this is going to be quite boring because 2 is the smallest number. But it's going to check, is 2 smaller than 6? No. Is 2 smaller than 4? No. Is 2 smaller than 6? Is 2 smaller than 3? Is 2 smaller than 4? And it'll work its way down through that. So I'm going to speed this up slightly here. And what's going to end up happening is we're going to get to the end of our inner loop. We're going to get all the way down to the last value here and say the smallest value is in position 2. And then we have a slightly redundant swap where we're going to swap the value with itself. And then we move on to the next position. So we know that number 2 is exactly where it should be in that sorted array. And we move on to sort out the value 6 in index 1, where we can easily see if there are different values that should be there before 6. Excuse me. Okay, so we're almost at the end of the inner loop. It's 10 less than 10. No, it isn't. So our inner loop is finished. We are now going to swap 2 with 2. And then we move on to run the inner loop again. I is going up to 1, which means j will start at 1 plus 1, which is 2. So we're checking from position 2 onwards, because I'm currently here. Everything above where I currently am, where index I is, I can guarantee is already in the sorted value. I'm going to check, okay. So it's saying here, so far, the location of the smallest number is in index 2, but now we're going to see that 3 is smaller than 4, so index 4 becomes the location of my smallest value. And then it continues on through the rest of the loop. And it works its way through the rest of it. And then what it's going to do is it's going to swap the value inside index 1 with the value inside index 4 to put 3 up here. So you can see that the swap function now is actually going to move 2 of the numbers. And now we have 2 numbers in the right position that we can verify. Anything, we're currently at position 2 working our way down. But anything above that, so position 0 and position 1, we can verify. Anything below that, 3 down to 9, it's possible it's in the right order, but we cannot verify that. So it's going to work its way through. You can see in this scenario here that the next smallest value is going to be 3 again. So we're going to be moving 3 into index 2, but I have to get to the point where it's finding that. What you will see as we visualize this is very often that the action of bringing the smaller numbers earlier in the array will automatically put some of the larger numbers in positions that they should be. That's a coincidence. That's an unintended side effect. What we're only concerned with is putting the smaller numbers at the beginning, because we can't guarantee that. We can't guarantee, that we're going to place the larger numbers at the same time as rearranging a smaller number. We can only guarantee we're putting the small numbers in the right position. That's why we have to check every element in the loop. And so it's going to swap 3 there. And we move on to the next one. And I'm going to speed up the animation ever so slightly, otherwise we can be here for another 10 minutes. So the code's going to be doing the same thing, which is, again, this repeated action of, are you smaller than what I currently think is the smallest value? If not, move on to the next number. If you are, well, congratulations, you're now the new smallest number, and we'll move on to the next number then. So currently, I think an index 5 is the smallest value, which I believe will be the case. And I can see from looking at the array as it is now, I have 1 number to move, and the entire array is in its correct order. But the array will keep running. It'll keep checking through all of the other values. just going to work its way through this. And eventually it's going to move 9 to there. Okay, so at this point, if I were to, oh, actually, sorry, no, I have one more swap to do after this. And again, index I is at 5, so I can say that with 100% confidence, everything above index 5, so 4 up to 0, is in the right order. And what I can say about index 5 down to the end of the array is it has yet to be sorted. I can't make any other comment beyond that. And it's working its way through. So as this is finishing off, there's a couple of things that are worth noting. When you start the algorithm, you have the most amount of work to do because you haven't put any of the values into the right position. And every time the inner loop finishes and does a swap, you have one less space to worry about. So your algorithm gets faster as it gets toward the end of its running because we have less values to put in the right position. Because we're dealing with an array, which is a finite data structure, it's static. When we create it at 10, it stays at 10. Next year and second year, you're going to learn about dynamic data structures, where we can have them starting at 10 and growing to 15, and then shrinking back down to 11, and then growing up to 200. They're much more complicated to sort, but it's still possible to do that. So as it's working its way through, you can see that while it might have, if we have 100, I'm not going to do 100 here, but if we had 100 elements to sort, and let's say just by the way the elements are generated, when we've done the first 15 numbers, everything else is in the correct order. Each subsequent check is getting ever so slightly faster because we have one less number to check. So it's getting faster and faster and faster as it goes through the redundant checks. The other thing that's worth noting is, I am sure all of you could look at the code for that algorithm and suggest how it can make it a little bit better, how it can make it more efficient. Can anyone think of any? So the immediate one I would think of here is what happened in the very first iteration of that. The very first number in the array that I used was 2, which also happened to be the smallest value. But I still went all the way through the end of the array, nothing I can do about that. And then I tried swapping 2 with itself. I could have here an if statement that checks to see if I and SML are the same value. And if they are, do nothing. If they're not, it means I actually have 2 different numbers to swap, and I could then run that piece of code. It would save a small amount of time, but it would be a slight increase. Another thing that I could do, you see when we go into this if statement here, we go into this if statement here when we find a number that is smaller. It may be possible to add some sort of a counter variable here that if we don't find any other numbers that are smaller than what I'm trying to place now, that the remainder of the array is in the right order. Now, that's not 100% because you might have a smaller number. You might have all of the numbers on the right-hand side then larger than what I'm looking at. It doesn't mean that they're all in the right order themselves. But it's things like that that we could start to look at. In nearly all of these algorithms, you can look at them and go, well, that could be made a little bit better there, that could be made a little bit better here. What we look at now for the remaining 3 weeks is the classic iterations or the classic variants of these algorithms. There are, for almost every algorithm you can think of, if you go off to the library and you get there's lots of books you can look at. But if you look at a book of data structures and algorithms, it will go through things like linked lists and array lists and hash tables and heaps and maps and graphs and lots of different ways you can store information. And every single one of them has a variant where it's a little bit improved or it's a little bit more efficient for a certain type of data, or for a certain amount of data, or for a certain type of variable we're using. And the thing is that when you learn them the first time around, you learn the most general version of it. And as your skill grows as a programmer, you learn to look at that and go, oh, I only have a maximum of 10,000 values here. Do you know what? I'm going to stick with a simple version because the extra time and effort it is to run a more complicated algorithm won't actually make a difference in the time. Or I don't have just 1,000 or 10,000, I have 4 billion values to solve, or I have 15 billion values to solve. So in that scenario, I need to have the most efficient algorithm that I can use, and it's worth putting in the time and the effort. And that's just something you learn over time as you get more familiar with the problems. Last week at Google Next, which is Google's big kind of tech conference, the keynote started off with the CEO talking about a research student who had calculated pi to like 14 trillion numbers of accuracy by using Google Cloud and by having lots of different cloud nodes computing certain elements of it. So that's a massive, massive number to work through. There's another version of that, Rod. So that's another kind of like a hobby or a challenge inside computer science. What's the biggest, most accurate version of pi you can calculate? Another one is prime numbers. What's the biggest prime number you can calculate? And it's working out, well, how do we calculate that? How do I actually verify that, yes, that's a prime number, and no, that's not a prime number? And in the algorithm we've looked at already, the brute force algorithm, that's not really efficient. So the brute force algorithm, if you don't remember, was we take whatever number we have, number 15, and we're going to check from the number 2 up to the number 14 to see if any of those numbers divide in. If any of those numbers divide in, well then no, it's not a prime number. If none of those numbers divide in, yes, it is a prime number. And that works for small numbers, because the larger the number, the more divisions you have to do. We could make that much more efficient in 2 simple ways. The first one is understanding prime numbers. 2 is the only even prime number. So if we've got 17,013,000 is the number we're checking to see if it's a prime number or not. We could just check all of the odd numbers. We wouldn't have to check any even numbers after 2, because we can guarantee that 4, 6, 8, 10, none of the even numbers are going to be prime after number 2, because 2 divides into all. The second thing we could look at is if we have, what did I say, 14,013,000, or 17,013,000, whatever I said. Once you get to halfway plus 1, it is impossible for the upper half of the numbers to ever divide in even. Think about any division you've ever done. Go back to the number 15. Its divisors are 1, which we don't count for the prime numbers, 15, which we don't count for the prime numbers, and the other divisors are 3 and 5. 3 and 5 are both less than half of that number. Take any number you can think of, the number 39. Its divisors are 1, 3, 13, 6 isn't going to it, and 39. So 39 doesn't count as part of the prime numbers. 3 and 13 are less than half of 39. So if you think about that, we could half our search space by only dealing with odd numbers, and then half that search space again by only checking to halfway plus 1 of whatever number it is. And that's an example of how we can look at a very basic algorithm and go, oh, I can make that a little bit better. Beyond first year, but that's kind of what we look at here. Okay, or what we would look at over the next couple of years. So, selection sort is a common sense algorithm. If I were to give you a list of 100 numbers on pieces of paper, like individual cards, and ask you to put them in the right order, selection sort is basically what most people do as their first option. If you can only sort one number at a time, it's kind of how people do it. I pick the card up and go, no. Oh, right, okay, move that over to here. Okay, so that's why it's considered a common sense. It's really only effective for small amounts of data. As we increase the size of our data, we increase, not linear, we increase quadratically the amount of time it takes to search. So for every time we have, if we've got 10 elements, it's going to be basically 100 checks we have to do inside that. If we've got 100 elements, it becomes almost 1,000 checks that we have to do. And the reason for that is that our inner loop goes from 0 to 1 less than, it goes from wherever we are to almost, so from almost the entire array each time. And that's not a particularly good loop structure. The loop structure anywhere, the double loop structure is always going to be inefficient. Because as we scale up those numbers, if we've got 1 million elements to sort, it means that we almost have 1 million by 1 million to actually calculate what we're looking at. The other big problem we have, which we saw in all of our examples, is the algorithm has no way of recognizing when our data set is sorted, which means that it's ineffective for partially sorted data. Okay, so that's an overview of our selection sort. What is worth noting is that selection sort and all of the algorithms we're going to look at are what are called in-place sorting algorithms. And what in-place sorting algorithms basically means is we start off with one array and we do not need to create a second array to hold our new values in. We sort the values within the array that we're given. The argument to move to use in-place sorting or to use an out-place sorting where you can create a duplicate array depends on what resources are available for you. So we could create a sorting algorithm that essentially creates a dummy array of the same size as our original array and just adds the values in. Okay, so it just goes from wherever we are, so it would just be the inner loop. Now that would be exponentially faster, okay? But the problem is it depends on what resources we are. When this algorithm was created, space on your machine, the amount of memory, cache, RAM that your machine had was finite. And so it was considered that in-place sorting is a more efficient way of doing it because memory is so expensive that we don't want to be creating duplicate amounts of information. If you've ever done video editing, usually you end up with what's called a scratch drive, which is where you load up the master, and if you have any duplications, if you're reusing a scene, so you have an awful lot of data that gets added onto a hard drive that as you're editing through it, just gets a duplication, we edit it down, we add it into the final version, and we delete that off. So there's an awful lot of reading and writing to our hard disk. Especially with solid state drives. There is a finite amount of times you can read and write to a solid state drive before it starts to degrade in quality. You can essentially wear out the circuitry that allows you to add data to a drive or to read it from a drive. With the problem initially with spinning hard drives was the time. They're slow. So if you had to write information or read information from a hard drive, it took an unacceptable amount of time to get the information to or from that hard drive. It was better to be clever about how you store the data. So you store less data on your RAM, you can do that. With SSDs, we have a bigger issue that if you have a drive that's continuously being rewritten to and read from, you can, over time, now we're talking about millions of reads and writes in each sector, but if you have something running continuously, if you have a cloud server, have you covered anything about cloud yet, here? No, okay. So the idea of a cloud is it's moving, rather than having, this is my laptop, all of my software runs off here, or this is my web server, it's inside my company. All of our resources run inside here. It's moving that same power off premise. You pay Google, Amazon, Microsoft, whomever it might be, to use processing power, to use software management. So you don't need to worry about having a room with huge fans for cooling systems because you're saying, well, no, I'm just paying someone else to do that. I don't need to have the premise to do it, but I pay €100 a month so that I can have all of the resources I need. But if you think about the way cloud, one of the big premises for cloud is elastic. It grows and shrinks depending on what you need. if I have a super successful blog, but just for 1 month, and it's hosted on a cloud, it will grow so that I won't get a timeout. Everybody who tries to access my blog will be able to access it. And as people stop visiting it, it will constrict back down to whatever it needs for that resource. And that's really good because it, again, it's saving us having about, I need to go out and buy a new server, I need to go out and buy a new switch, I need to go out and buy 10 new machines, because it's doing that for us. But that's a huge hassle to do it on premise. So having it in the cloud means that anybody might be using that hard drive depending on who's in demand each day. So you have continuous reading and writing. And the hard drives are continuously being swapped out of the cloud storage because they're essentially getting worn out from the amount of reads and writes. Or why was I talking about that? Oh, because of in-place sorting. So in-place sorting means that we are keeping our memory small for that algorithm, which means it's more likelihood it stays all on our cache or our worst case scenario on our RAM, so that we're able to actually deal with it that way. It's faster and it takes up less footprint on the machine. Okay. How are people feeling about selection sort? Any questions so far? Okay, so I'm going to ask you a question then. So far in this class, I have talked about and I have demonstrated ascending sorting, starting with the smaller numbers at the front and bigger numbers at the back. But I mentioned at the very beginning that the other way I might get you to rearrange things is to do a descending sort, larger numbers at the front, smaller numbers at the back of the array. Based off of that block of code, what would I need to change? Before you say anything, we don't need to worry about the name of this variable. We know that's the one we tried to place. Okay, so we can just you can assume that for descending sort that will be called biggest location or largest location. But from a program point of view, what would I need to change in that piece of code? So here.
Yeah.
Okay, so just flip that to the other way around. Anything else?
Plus one to the minus one.
This one here. So from +1 to -1?
Yeah.
No. And the reason why we wouldn't is because this loop here is going from my current position to the end of the array. It's not got anything to do with where the numbers end up sitting. It's just where do I have left to check. So if you're doing -1, you're checking from my current position back to the beginning. And if we were to do that, we'd need to change some other stuff here as well to make sure we're working back towards 0. Okay, so Dawn is suggesting we just change this one symbol here, and that should do it. Can anyone add to that? Take away from it? Add a clause? No problems.
For the minus, the length -1.
Yeah.
That has to be changed because you still have to check the last one.
No, we just like we're trying to say in there, we can actually leave that where it is because again, the loops don't have anything to do with the numbers. The loops are just where we check. They don't have anything to do with the ordering.
Okay.
So, Don, you're absolutely right. The only thing we need to change is that single statement there. Okay. So if I go back, and I was going to run at full speed now because I don't really want to. I'm going to shorten out my my array as well. I need 10 elements. So get rid of all these elements here. Okay, so I have a much smaller array now, and I'm going to change this from greater than to that. Compile it. My lies up front. Okay, so I have this running full speed, but you'll be able to see that it'll start searching down through it, and it will pull the larger values to the beginning of the array, automatically moving the smaller values toward the end, but we can kind of guarantee that the larger values. So you can see the 6 has been put in the right position here, and then it's going to end up moving this 6 to position 1. Four is okay where it is, and then moving 3 down to position 3. Okay, so it's very, very simple. In all of the algorithms we're going to look at, there is an if statement somewhere. It's our comparison. You have to have an if statement inside your sorting algorithms, because otherwise, how do you know what order they should be? Okay, so in that, no, that's done. So in the if statement, wherever it is, changing that would be the only thing we need to do. Okay, let's go back 2 slides there. Everybody still okay? Yeah? All right, okay, cool. You sure? Because we're going through this stuff fast. So if everyone's okay, that's fine. I'll start on bubble sort, which means that we will finish up a little bit earlier today, but also we'll finish up a bit earlier of new content for the semester. We'll have more time for revision as well. Okay? You're not just being quiet because you want more revision classes, is it? Okay. This will make more sense when we start to look at the bubble sort algorithm. There are 2 types of questions I ask when it comes to sorting algorithms. Because all we do is say, here's selection sort, here's bubble sort, here's insertion sort. We explain what's happening, but we don't do really anything else with it. There's no continuous assessment on it. There is no assignments for it. There's no class test for it. The only place where you're assessed for this in first year is in the May exam. And it's the last topic, so I can't ask a huge amount on it. So 2 types of questions. The first type of question is, I give you a block of code and I ask, what algorithm is that? And you have to be able to tell me, is it selection sort, is it bubble sort, or is it insertion sort? And I usually then ask what ways to sort in the algorithms, so ascending or descending. Or I ask the opposite. I give you a block of text. Write a method to use selection sort to sort an array of numbers into ascending order or into descending order. And so you have to start from a blank page and build up the code. All right? The trick to looking at a block of code and discerning which algorithm you're looking at is where the swap statement is. Okay? So inside selection sort, our outer loop starts, our inner loop starts, our inner loop finishes, and before our outer loop finishes, but outside of our inner loop, our swap statement is here. It is not in that location for either of the other 2. Each of the 3 algorithms we're going to look at have the swap statement in a different position. And for me, when I was looking at these algorithms the first time around as a student, that's how I did it. I paid attention to where the swap statements are. And so when I glance out, go, it's outside the inner loop, it's inside the inner loop, it's around the inner loop, and I can be able to tell you which one it is very quickly from that. If you're given a blank piece of paper, or if you're given like a description, write bubble sort or write selection sort in this order, you need to remember what you're doing. So what I would do is I would take this block of code here, and I would write, actually you're not even that, I would pay attention to the algorithm can be stated as following. From my current position, find the smallest element in the remaining part of the array, swap with my current position, move on to the next number. That should be enough for you to recreate the code almost perfectly. The 2 mistakes that students make is in selection sort, they very often leave out this, the -1, or they leave out this, the +1. This one, not that big a deal. It adds 1 extra search for every value it is, because there's no point in checking if my number I'm going to check is that smaller than the number I'm already checking. That's a little bit ridiculous, but it won't break your code. If I leave this one off, it will break the code, because I'll get an array index out of bounds on the very last, because it'll try to go all the way up and say, okay, in index length -1, so the last index we have, check the number to the right hand side of that, and there's nothing there, so it'll crash the program. So I would suggest not forgetting either, but the first one here is the more important one, because that will actually crash your program. Okay. We'll do About 20 minutes on this, and then we'll finish up a little bit earlier today. Okay? Bubble sort. So selection sort is from wherever I am now, search the remainder of the array, find the smallest value, swap it with my current position. That's what selection sort is. Repeat until I hit the end of the array. What bubble sort is I take a pair of numbers, so index 0 and index 1, and I check are they in the right order. And then I move that window, that pair along. So I go 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, all the way up to the end. Whenever I find a pair that are the wrong way around, I swap them. Okay? If I don't find them the wrong way around, I leave them as they are, and I move on to the next pair. Does that make sense? It's a little more complicated of an algorithm. They are each increasingly more complicated. So it's called bubble sort because the larger numbers bubble to the start to the end, or it can be called the sinking sort because the smaller numbers sink to the start of the array. But essentially, what you're doing is you're taking two neighbors and you're checking are they in the right order. This performance can be improved by modifying it to have a bidirectional bubble sort. In other words, first pass front to back, second pass back to front, third pass front to back. We're not doing that. Just it's highlighting again that all of these have variance. So here's our code. The outer loop should be familiar because we're going to -1 to the second last index. The inner loop is kind of confusing. The middle section of the inner loop, it's where most people get this wrong or make a mistake. We're going to start from the beginning of the array. We're going to go all the way up to the length of the array, -1, minus I. Okay, so the length of the array is the total size of the array. -1 means we're going to go up to the second last index. And minus I. Can anyone think why we have minus I there?
You have to come back 2 spaces there.
It's going to grow. It's going to start with, it'll be, let's say we have a 5-element array. So we're going to check, well, j is less than 5 minus 1 minus 0. Then it's, well, j is less than 5 minus 1 minus 1. J is less than 5 minus 1 minus 2. So can anyone think why I have the minus I there?
Because the bigger number is already from the
Exactly. Exactly. If you think about selection sort, the inner loop always started after all of the sorted part of the array. So we'd say, wherever I am now, everything on the left-hand side is sorted, everything on the right-hand side I've yet to check. So I'd never need to check the sorted part again. Guaranteed it was always in the right position. Bubble sort works the same idea. But because bubble sort is, rather than dragging the small numbers back to the beginning, it's pushing the big numbers to the end. It means that every time the inner loop finishes, we have one more number at the end that's in the right position. So we start off with, we go all the way to the end because none of the numbers in the right position. And then we go back around again, I goes up by 1, we have one number in the right position. So I, the value of I, is going to give you an indication of how many numbers are correct at the end of the array. So just make sure you're not checking through values that are already sorted. And then here's our check. If the value, if the value j is bigger than j plus 1, so if the number on the left-hand side is larger than the number on the right-hand side, swap them. If the number on the right-hand side is larger than the number on the left-hand side, do nothing. Just move on to the next pair. And you can see here, our swap function is inside the inner loop. So, selection sort, our swap function is after the inner loop. Bubble sort, our swap function is inside the inner loop. Bubble sort and selection sort are very similar in their code. They have very, very minor changes. It's almost like, if you think about what we have, we have two loops in both of them, we have an if statement in both of them, we have a swap in both of them. So they're all very, very similar in what we're going to do. Let's look at an example here. So here's our initial array. Okay, so you can see we've got our 6-element array here. We're going to take a pair of numbers. We're going to take 3 and 6. Is 3 bigger than 6? No, it's not. Okay? Take the next pair. 6 and 5. Is 6 bigger than 5? Yes. So we're going to swap them around. So 6 goes into this position. And then we check to see the next pair. So 6 and 12. Is 6 bigger than 12? No. Move down here. 12 and 17. Is 12 bigger than 17? No, it's not. Here, 17 and 8. Is 17 bigger than 8? Yes. So we're going to swap them. So the next time round, you can see that 6 has been swapped. And where are we? 17 has been swapped as well. So there were 2 actual swaps in the first pass through our loop. This is one pass through the inner loop. It's gone from start to completion once. We can guarantee that this number here, the one number at the end, is in its right position. Any other numbers here that you might be able to look at and go, oh, that's in the right position, that's in the right position, that's in the right position, that's coincidental. That's not because of our algorithm. That just happens to be the way it is to the numbers that were selected. So we start again. We're going to go all the way down, but we're not going to bother checking this number because we know that number is in its right position. So 3 and 5, they're good. 5 and 6, they're good. 6 and 12, they're good. 12 and 8, they're not good. So we need to flip those. So you can see here we flip them there. And it doesn't bother checking 12 and 17 because we know 12 and 17 is good. At this point, I can see that that is already in the right order. But I'm going to end up checking it again. So I will check again. The algorithm will keep running. 3 and 5 are good. 5 and 6 are good. 8 and 12 are good. Or sorry, 6 and 8 are good. Back again. 3 and 5 are good. 5 and 6 are good. 3 and 5 are good. We're done. So you can see that in this algorithm again, there is redundant checks. We have the advantage of having a very small amount of numbers to look at here, and we at a glance can go, oh yeah, they're in the right order. But our program does not know that. You go back to one of the very first things I told you about computers. The computers are stupid. They are really, really good at following instructions, but they do not have any common sense. They don't have any ability to go, do you know what? My job's done here. If you give it a task and say, you will do this until this condition is true, it will keep doing that. Even if the data it's searching through doesn't need any more changing. It's all correct. So it'll just follow the instructions blindly until it hits whatever the condition is, and it'll finish that inner loop.
Luckily.
Beg your pardon?
Luckily.
Luckily, yes.
Yeah.
Well, yeah, honestly, it is luckily, because again, the examples I use here are nice small. If I had 5 million elements, you wouldn't glance at it and go, oh yeah, they're all in the right order. Because you wouldn't be able to tell. There might be one right in the center, which is 2 digits are off, and you wouldn't know. But if you have blind following, it will go through it. And then, yes, it might take a while to run that code and sort the values, but you can guarantee at the end that all of those numbers are in the right order because it has not taken an assumption. How many of you, as you've been working on programming problems, have had an error in your code that you just could not see where it was? And you look at it, and you look at it, and you look at it, and you could be there for 5 minutes, 10 minutes, an hour, 2 days, a week. And you ask somebody else, me, one of your classmates, someone else, and they go, oh, it's there. Immediately. Good, that many of you, right, okay. I still have that problem, okay? You get a little bit better at it, but it's the reason why someone else can spot your error much quicker than you can is because they didn't write the code. They're looking at it and they're not assuming they know what it's doing. When we read our code, or for me, when I read my paragraph of English text with the document I've written, the reason why I've missed the grammar mistake, the spelling mistake, the code mistake, is because my brain is thinking. My brain's going, oh, I know what this should do, and it's seeing most of the code there, and it's kind of it's almost as if I'm skipping over that error over and over and over again, and I just can't figure out where it was. I had a final year student who last week when I met him was really, really stressed out because he was trying to do something with Google Drive. It just wasn't working. He couldn't figure out what it was. It wasn't working. He was getting really stressed out about it. We were getting toward the end of the semester. All the pressure's building up. Final year, everything comes toward the grade. Madam today has jumped forward in what has been done on the project. Huge, huge jump. And all it was is that in the installation of one piece of software, he had missed one step. But because he assumed that all the software was installed correctly, he had spent hours, if not days, looking at his code, assuming there was something wrong in the code. Okay? Because the assumption that, oh, I followed all those instructions correctly, I didn't skip any of them. We are great at giving ourselves the benefit of the doubt. Of course I did everything correctly. Computers don't do that. They just follow the instructions, okay? So if you think about it, if you live with somebody and you ask them ever to do something, and then you can go, oh, did you do that thing? And they go, and they have to think about it, or they go, yes, and they go, no, you didn't. Computers don't do that. If you ask them to do something, and you've asked correctly, you've asked in the right syntax, they will just go and they will do it. Okay. So this implementation is going to starts from the front and moves the larger values to the back. Each pass of the array goes and puts at least one item in the correct position. We can only ever count on it putting one item in the correct position. It nearly always puts, throughout the lifetime of that algorithm, it puts more than one in the right position as it's working its way through. But we can only ever say with 100% confidence that it puts one item in the correct position each time around. It does n-1 passes, and again, very much like our selection sort, the reason why it doesn't do n passes is because if you sorted 9 of the possible 10 numbers to put in, it guarantees that the last number is already in the right position. If you can say the other 9 numbers are absolutely in the right position, well then you don't need to check the 10th number because it is in its right position. We already kind of talked about that. Okay. So let's do a quick recap and then we'll finish up a little bit early. Okay, so selection sort. Selection sort is the easiest algorithm to look at. You are going to take an array of which you cannot guarantee at the beginning that the values are in the correct order. You're going to start at the first value and you're going to check every value to the right hand side of that to make sure that you have the smallest value in that array. If through your searching through the array, through the remaining values in that array, you find a value that is smaller, you keep track of its location. When you hit the end of the array, you swap the value of the location of the smallest number with the value in the location you're trying to set. So first position with the location of the smallest number. And then you move on to the next position. And you repeat that until you've searched, so you've placed n-1 of the numbers in the correct position, guaranteeing that the last number is in its right position. Our code requires us to go from the beginning to the length -1. Every time we start off by saying the current number must be our smallest number because we haven't checked any others. That's the only thing we can say for certainty. We are then going to check every number to the right-hand side of that all the way up to the end of the array. Whenever we find a smaller number, we're going to say, okay, I'm going to keep track of that smaller number. At the very end, after the inner loop is finished, after I've checked every single remaining value, so I can guarantee I know where the smallest number is, I'm going to swap my current position with the smallest position, putting that smallest number in its correct position in the sorted part of the array. That is selection sort. It will nearly always have a number of redundant passes through, where the numbers are already in the order, or that specific number is in its correct position. But we can't do anything about that. Our bubble sort algorithm takes a pair of numbers. It starts off with the first number and its nearest neighbor, which is the second number, and it checks, are they in the right order? Is the number on the right-hand side larger than the number on the left-hand side? If the opposite is true, if we find that the left-hand number is bigger than the right-hand number, we switch those numbers around. And we move on to the next pair of neighbors. We move on to, if we start at 0, 1, then we move on to 1, 2, then we move on to 2, 3, then we move on to 3, 4, and so on. Whenever we find a pair of numbers that are in the wrong order, we're going to swap them immediately. It might mean in selection sort, we only ever perform the swap function once per inner loop, or per iteration of the outer loop. We check all of the numbers and then we do one swap for each number we're trying to replace. It is very possible in a bubble sort that we could have a swap for every single number in the array for at least the first time around. Because as soon as we find a pair that are out of order, we're going to swap them, we're going to swap them, we're going to swap them. And we're going to work our way toward the end of the array. Our inner loop will go to the length of the array, -1, minus the value of I. And the reason why we go to the minus the value of I is the value of I is an indicator of how many numbers are in the correct position. So since we're pushing the large numbers to the end of the array, we don't need to go to the end of the array each time. We're going to start at the beginning every time, and we go almost to the end, slowly getting closer and closer and closer to the beginning of the array as we finish our sorting out. In selection sort, our swap statement is outside of our inner loop. In bubble sort, it is inside our inner loop. It's worth remembering that. And for both of our algorithms, if I wanted to change it from ascending order to descending order, the only thing I need to change is I need to flip that symbol the other way around. That's all I need to do. Okay. We have rocketed through that content. You have taken a week off of my initial timeline, which for you guys means that we have more time for revision. Okay. This is the 16th of April. Next week is 23rd, which will be our last week of new content. And then for the last day of April, 31st, is it 31st? 30th. Will be our last class of the year, or sorry, last class of semester. Will be a revision class where I'm going to talk about the exam paper, talk about the structure of the exam paper, go through the type of questions that are asked, and then I will have an additional class the first week after semester finishes, so the 6th of May, or the 5th, I can't remember what it's going to be, which will be a revision class where again we'll work through some exam type questions. Okay. So, before we finish up with this content, does anybody have any questions about either selection sort or bubble sort?
Well, I'd like to see this minus I in Juliet maybe.
Yeah, absolutely, absolutely. Well, I'm getting that set up. If anybody has any questions, shout them at me.
Would there be a reason to pick one over the other if you're just working on like a small set of data?
When we're talking specifically about these two algorithms, no. It is the one you can get up and running fastest. Okay, so this one here is going to go, check there, it's going to go from that there, that's fine. This one here, J, is going to go from 0. Don't need this. J is going to go from 0. It's going to go to the length of the array, -1 minus I, J plus plus. And then what we're going to say here is if J is larger than J plus 1, then we're not going to have that code. We're actually going to take sorry, I just need to tidy up this code because I have different variables in here. So that's going to be J. This is going to be J. No. J plus 1. And then this is going to be J plus 1 T. Okay. Got everything there.
We need to set an array.
Yep, I have it up there.
Ah, yeah.
The small array up there. Right, let's test this one. Let's scroll the animation down. Okay, so this is going to do basically the same as the previous one. Set up our array, put our values inside there. We are going to then start at the beginning of the array. So start at 0. We're going to go to the length of the array, which is 5 minus 1, give us 4. So we're going to index 4, or what's less than index 4. We're now going to start from 0. We're going to go, and you can see here what's going to happen is we're going to check the length of the array, 5 minus 1, 4 minus, in this scenario here, 0. So the first time round, we're going to check pairs all the way to the end of the array. So we're checking to see if 2 is larger than 6. No, it's not. So we go on, we move it forward. I is now 1, so we're going to go. Oh, sorry, I is not 1 because we're still in the inner loop. So here we're going to check 6 and 4. Here they are in the wrong order. So 6 is larger than 4. And so it's going to swap the positions. It'll put 6 into index 2 and it'll bring 4 to index 1. So it's pushing that larger number toward the end of the array. And then we move on. We're going to have 6 and 6. One's not larger than the other, so we don't do anything then. So just nothing then. But then we're going to have 6 and 3. 6 and 3 obviously are in the wrong order, so we're going to swap them around, pushing this 6 to the end. And once this swap statement is finished, we have finished one complete pass of the inner loop. Since we've completed one pass of the inner loop, or one complete pass of the inner loop, we can say that one value is in its right position. So 4 is not less than 4. And we're going to increment I, so I is now 1. So now you'll see that it's going to go up to this position here, and the inner loop, the j plus 1 will end up checking here, but we don't bother checking this position. So it'll be 4 minus 1 minus I, 1, there's 3. And again, it's going to work its way through. It's 2 larger than 4. No, it's not. So we move on to the next one. Here we can see we're checking to see is 4 larger than 6. It's not going to be. So we'll move on to the next one then. But then we're going to have a 6 larger than 3, which it is. And now we're placing our second number in there. You can see that as this loop is going to finish, we realize we're at the end of the array as far as we're going to go. So it's 3 less than 5 minus 1 minus 1, which gives us 3. Is 3 less than 3? No, it's not. And I goes up by 1. So now we can see that I is the value of 2, which symbolizes we have 2 values in the right position at the end of the array. And we're then going to work our way through. And we can see by looking at the remaining status of the array that we really need to swap these 2 values here around to get the array in a complete sorted order. But we're going to go through it methodically to be able to swap our values if required. So it's 2 larger than 4. Nope. So let's move on. we're now going to check is 4 larger than 3, which it is. And then I'm swapping the position of 4 and the position of 3 to put the values in their correct order. Okay, so now we can see by looking at it that all the values are actually in the right position. However, we need to finish out our inner loop first. So we can see that 2 is not greater than 2. So we go on to the next one. I is 3, so we can see that we do have 3 in the right value, and we're now trying to just make sure that these are in the right position here. So with 0 less than 5 minus 1 minus 3. 1, so 0 less than 1, it is. So we're only looking at these 2 numbers here. These 2 numbers are in the right order, we're done. And then our loop will finish. So at this point, it's just tidying up the outer loop to say that we're finished the algorithm. Okay. That makes sense? Cool. Anyone have any questions at this point? Everyone's happy enough? What we'll end up doing next week is we'll go through insertion sorting. It's the most complicated what we're looking at this year, and then I'll do a recap of all 3 with code examples, just so you can see the money. When was your submission date? Was submission date yesterday, was it, for the workbook 2? Have you submitted it? Yeah. Great. Okay. Have we all submitted it? No. Right. Okay. Get it submitted this week. If anybody needs, if you've already submitted it and you want to utilize the time remaining this week, you can resubmit. That's fine. There's no cap on the resubmission on it. I would suggest, since it's only worth 5%, if it's up, leave it alone. You probably have other assignments that are more weighty that you can spend time on. That will be the last thing that I'm going to correct because it's going to have the least effect on your grades. The next piece of work I'm going to correct for you will be your class test, because that's going to be the most direct influence on what the May exam is going to be like for you, because it's the same test environment. And then after that, obviously, I think it's the 25th or the 26th that I set as your deadline for the last assignment. But sometime toward the end of the semester, it might be the Monday, the first week.
There isn't an upload for that yet.
Well, then I probably should put one up. So, what I will do is I will say it will be Monday the 29th, yes, whatever the last Monday of term will be. It'll be that Monday, so it'll give you the weekend to work on it. Again, as a group, if you decide, you know what, if you can push it to the first Monday out of term, I'm fine with that. It just means you won't have your grades before we finish our revision classes. You'll have your grades before the exam, you just won't have your grades before we finish the revision classes. Okay? I've also put up the Excel spreadsheet where you can throw in the grades you have already to see where you're sitting on that course. Okay? Just to quickly highlight what that looks like. See that? Grade. No. So let's find it here quickly. Grade calculator. It's been moved. Brilliant. Okay. Yeah, better download it again. So I probably put it up in the forum. You here end up putting it up. Grade calculator. Okay. So the way it's factored in is as you get your grades, and you haven't obviously got all of them. Let's say you have your workbook 1. Let's say I got 90 for let's say I got 90 in that. For the word manipulator, let's say I got 71 in that. class test, or work with 2 I haven't submitted. Class test 1, let's say I didn't do well, I got 45 in that. Zombie dikes, let's say I got an 80 in that. And then class test 2, we haven't got our grades. Oh, that's not updated. Oh, yeah, okay. Nope, that's not right. I will re-upload this with the proper grading on it. Okay, but what will happen is it'll spit out where the grades go here, okay? So the way this works is if you notice 5, 10, 5, 10, 10, 10, 20 totals to 70. You have 70% of the total subject is based on your continuous assessment, 30% of the examination. So what will happen is it will tell you out of 70 what's your grade, but then it'll also tell you out of the 100% for continuous assessment what's your grade there. If this number here is above 40%, you've already passed your continuous assessment. If it's below 100, or if it's below 40%, remember that you have not received the grades for this yet, or for this, or for this. So there's absolutely the possibility of jumping up massively. I will remind everybody again, even if this number here is above 40%, you still need to sit the examination in May. It is impossible to pass this subject without passing the examination. Okay, that goes for every subject in Griffith, but just since I'm teaching you programming is one of those examples where we do so much continuous assessment that it's worth so much of the total subject. It's very easy to get kind of a 60% here, 50% here, and then whatever you get from the examination, even if your exam grade is below 40%, then it looks like you passed the subject because the total subject grade is above 40%. Unless both the exam and the continuous assessment are above 40%, you have not passed. Okay? This will be made clear to you once the May exam results come out, just so that nobody thinks that they're free and clear. In the scenario where you have to repeat an element, you will be informed by the faculty, hey, just to let you know, in computer programming, you need to repeat the exam. The exams will be in August. Or in foundations of computing, you need to repeat the continuous assessment. The continuous assessment is in July. Okay? But I don't want anyone feeling overconfident and going, oh, I don't need to turn up the exam in May. You do. You all need to turn up the exam in May. If that doesn't go perfectly, well, then we can deal with that with the repeat sittings, but don't miss an opportunity on sitting it, because nothing's going to be worse than finishing the course first week in May, having your exam on, is it the 15th or the 20th? It's sometime toward the end of May. Or not taking that opportunity, because if you have the exam on the 20th, you maybe have a 2-week gap from when we finish class contact to the exam. Statistically, students are far more likely to pass in May than they are in August. And that's only because the gap between when you actually had a class on that topic is much, much larger in August. And you're only studying independently. You don't have class contact time over the summer. So it is absolutely in your interest to make sure you turn up to all of the examinations in May. If something happens and you can't, that's a different scenario. But don't, because you made a mistake of, oh, I'm above 40% here, I don't need to sit the exam. Don't miss out on the sitting. Fair enough? Okay, all right, we will finish up there. Oh, we didn't actually finish that much earlier. We'll finish up there for today. Like I said,